Okay, x plus 1, the quantity squared. Okay, when we multiply that by x plus 1 to get x plus 1, the quantity cubed, Kaya, what do we get?
I got x cubed plus 3x squared plus 3x.
When we multiply that by x plus 1 to get x plus 1, the quantity to the fourth, Sydney, what do we get?
I had x cubed plus 4x cubed plus 6x squared plus 4x plus 1.
Okay, now some of you are already talking about what you thought this was going to look like before you even multiplied it out. Look at those coefficients. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1.
Oh, it's like a triangle thing.
Pascal's triangle.
Pascal's triangle.
Oh, no.
I hate
Why?
They did.
You didn't teach us. Definitely did.
Told us to skip over. We used to fun, didn't we?
What's the pattern in Pascal's triangle?
You add the two together.
Okay, so like 6 and 4 make 10. 4 and 1 make 5. Okay, so like right here we would have a 15, a 6, a 1, a 20, 15, 6, and 1. Okay, so the first and last number are always 1. Okay, and then everything that we get from in the row, we add the 2 diagonal from it. Okay. What does Pascal's triangle have to do with multiplying binomials? Pascal's triangle, I'm not sure why that got stuck there. Pascal's triangle describes the coefficients of x plus y to the n. And if I don't have to multiply 7 binomials together, that's kind of nice, right? Kind of. I don't want to multiply 7 binomials together. 4 is enough work in itself. Okay? So if we can follow a pattern, instead of actually multiplying 7 binomials together, yeah, me too. Me too. And that is the purpose of what we're doing today. Instead of having to take x plus y, or whatever it is, to a power greater than 2, instead of having to multiply, we can use patterns to figure it out. Okay? So this is the binomial theorem. On the next slide, I'm going to have the binomial theorem. What does, is every binomial going to look like this, x plus y? Yes. It could have coefficients, okay, and we'll talk about that. But what happens, because on the slide before I had x plus 1, and that was pretty easy to figure out. Well, what if that 1 instead is a y? What does that mean about the powers of y, and what happens to those? So on the next slide is the binomial theorem. I want you to write it down first, and then we will talk about it. So the binomial theorem is what it's called, and then I'm scrolling down so you can see all of it. sigma thing mean? The sum. Okay, so we're taking the sum of multiple terms. Okay? So whatever you're being raised to, that's what's going to go in your combination. So if you have a binomial raised to the 4th power, you're going to start out with 4 combinations of 0. And then your next term is going to be 4 combinations of 1. And then your next term is going to be 4 combinations of 2, etc., etc. Okay? And as you go through each term, okay, the powers of your first variable will start big and get small. And the powers of your second variable will start small and get big. Okay? So, like if we have n as the 4th power up here, then we're going to start out with x to the 4th power, y to the 0 power. And our next term would be x to the 3rd power, y to the 1st power. And then our next term would be x squared, y squared. Okay? No matter what, those two are always going to match, whatever combination you're using and the power of that second variable. And if we look at these right here, those are always going to add up to be what? If I add those two together, what do we get? N. That's always going to add up to be whatever n is. Okay? Now, I'm going to demonstrate how this works. For many of you, it'll be a re-demonstration. Okay? But over here on this slide, I'm pretty sure we were talking about these being the coefficients, right? But over here, I'm telling you it's a combination. What is happening? Pascal's triangle are combinations. Just look at them for a moment. There, I'll put them even. I don't know how they got uneven. But like this row right here. 4 combinations of 0 is 1. 4 combinations of 1 is 4. 4 combinations of 2 is 6. 4 combinations of 3 is 4. And 4 combinations of 4 is 1. Okay? So each row of Pascal's triangle are the different combinations depending on what row you're talking about. Here we have combinations with 2. Here we have combinations with 3. Here we have combinations of 4. The next one we would have 5 combinations, 0, 5 combination 1, all the way through. Okay? So we are using Pascal's triangle, but I'm not going to make you like sit there and memorize Pascal's triangle and like write it all down so you can figure out which coefficients to use. Okay? That would also not be a very efficient use of our time. Okay? But what I want you to understand is that Pascal's triangle, the numbers that we want to use are coming from these combinations. Okay? What do those look like up there?
Christmas tree.
They do, right? I will give you a Pascal's triangle Christmas tree sometime next week for you to color.
Sorry.
Why?
Yeah.
Just to decorate.
Like as a full flower tree? Shut up.
Not as a whole flower tree. Okay? Guys, let's talk about next week real quick before we get into our examples. Next week, we'll take 2 days to talk about 9.4. We'll take 2 days to study, and then Friday's our chapter test, and then your final is the following Wednesday. Write it down. 2x minus 3 to the 4th. You will get your final review for the weekend, next weekend. Okay, and then we'll have 2 days in class. Okay, I will wait for you to be quiet so I can start this example. Okay, so we have 2x minus 3 to the 4th power. Okay, what is n? So we're going to start out with, I gotta move this, 4 combinations of 0. Okay, whatever our first term is will be raised to the n power. And then whatever our second term is, what's our second term in this case? Ooh, good job. -3, because we were talking about x plus y. This is 2x minus 3. So we want -3. It's got to match this number to the 0. Is that 2 getting raised to the 4th power or just the x? The 2 and the x. Okay, so it is important that we think about that. Okay, then our next term. 4 combinations of 1. 2x will now be raised to the 3rd power, and -3 will now be raised to the 1. So that first term we're going to decrease the power, the second term we're going to increase the power. Okay, but remember, like I pointed out, whatever number this is, look up here as I'm pointing, whatever number this is in the combination is going to match this exponent, excuse me, up here. Okay, so our next term is going to be 4 combinations of 2 times, we're going to have 2x now squared because we're going to decrease by 1, and then the power of -3 will increase by 1. Four combinations of 2, 2x, oh, excuse me, I forgot to actually change that number. 4 combinations of 3, 2x is going to be raised now to the 1st power, -3 to the 3rd power, and then I awkwardly ran out of room, so we're just going to throw this guy here, okay? It's like a kindergartner writing, you know, and they spell like half of their name and then continue down here. You've seen that, right? Okay. 2x to the 0, -3 to the 4th. Questions on how I got any of those terms? Okay. Now, I know this seems a little bit tedious because now all we have to do is calculate all of these numbers, but you know how to do combinations in your calculator because we went out of order and we did combinations for probability and stuff. So, right here, we need 4 combinations of 0. 1. 2x to the 4th. So, what's 2 to the 4th? And what's -3 to the 0? Okay. Now, I'm going to be kind of obnoxious, and I'm going to find each one of these individually, but I want you to really know where these numbers are coming from. Okay? 4 combinations of 1 calculates to be 4. 2x cubed would be 8x cubed, and then -3 to the 1st power is -3. For this 3rd term, we have 4 combinations of 2. 2x to the 2nd, so it's 4x squared. And -3 squared is, guys, don't put that into your calculator, but if you do, -3 does need to go in parentheses. Okay? A negative number to an even term is going to be what kind of value? Positive. A negative number to an even power will be positive. Okay? 4 combinations of 3 would give us 4. 2x to the 1st, And then negative 3 cubed would be negative 27. And then our last term, 4 combinations of 4 is 1. 2x to the 0 is 1. And negative 3 to the 4th is 81. I don't have room for my parentheses, but you can forgive me, right? It's better than what happened prior. Okay? Now, you wouldn't have to do this red step for me because a lot of that could be done in your calculator, but I really want you to see that we have 3 individual numbers that we are multiplying together for one term. Okay? So our answer would be 16x to the 4th minus 4 times 8 times 3. 96x cubed plus what? 360? 216. Sorry. Couldn't hear you. X squared minus is that the 216?
Yeah.
216x plus 81. Okay. Now, I think that there is less room for error in something like this as opposed to taking 4 binomials and multiplying. Okay. Now on something like to the 4th power, I think this is quicker. Our next example is something to the 3rd power. May or may not be quicker. Okay. But I think that there is a less chance for error if you understand the binomial theorem as opposed to when you're multiplying and potentially mismultiplying, misadding, all sorts of stuff. Okay? Let's talk about this second example. Are there any questions before we go to that second example? Okay? How many of you vividly remember doing this in Algebra 2? Okay, those of you who aren't raising their hands, is it just a distant memory?
I just don't recall it all.
Really?
No, I do. I remember.
Yeah.
I don't remember the combinations. I remember sitting next to I was just recurring and figuring.
Okay, write down the second one. Did you say I remember crying?
Oh, definitely. Yeah, it was stressful. It was stressful time this semester.
Okay. I want this to be a low stress activity here. My goal is that this section is the less stressful of all of them.
It's actually pretty easy.
Okay, what makes this one a little bit different though?
X squared.
The x squared. Are we going to treat it any different?
No.
It's not special.
Have to be extra.
Okay.
I'm going to give you 2 minutes to work together at your pod to set up the 4 terms.
Oh, okay, yeah.
Did everything have you? You're gonna have your family.
Do I need it? Yeah. Am I allowed
Like what is it?
No, because I just don't know, because I have to.
Okay.
She said just shut it up. I'm about it. For the here,
Are you adding them? Power is the power remote.
And honestly, it just depends on the final. A lot of finals do that. It's different. No, we don't solve it. It's just-
As I've been walking around the room, this is what I'm seeing. Okay, that x squared is the first term, so it's getting that first power of 3 and then it decreases. 4 is that second term, so it starts as a power of 0 and then it increases. How do you know that you have reached your last term?
You know you reached your last term when it's to 0.
Like you have 3C3, right?
Yeah.
We can't have 3C4, like that doesn't make sense, right? When these two numbers match, I think that's a good thing to look for, Riley. When these two numbers match in your combination, you know you're at the last term. Okay? Okay. Like I said, you don't have to memorize Pascal's triangle. You can put the combinations in your calculator because you know how to do that. Now, the third row of Pascal's triangle is a pretty easy one to memorize, so if you know it, more power to you, but I'm not forcing you to do it, okay? This is probably what most of you are going to do in your head. I know that this is 1. I know that this is x to the, and I know that this is, so we have 1 times x to the 6th times 1. Okay? Plus, I know that 3 combinations of 1 is 3. This is x to the 4th, and this is 4.
Oh, next to the part.
Okay. 3.
It's x squared. 16.
So 3 times 16.
48.
So we have 48 x squared. And then last we have 1 times 4 cubed. Okay. Now, our final answer looks quite a bit different. Notice how our x powers don't go down by 1 each time. Okay. Our x squared powers went down by 1 every time. And so in our final answer, that just looks a little bit different. Okay. Okay. The last type of questions I will ask you, okay? I'm probably not going to make you multiply out like something to the 12th power or something to the 10th power. Okay, that's pretty excessive.
yes.
Right? How many terms are in our third power expansion? Okay, so how many terms would be in our 10th power extension? 11. Too many, I agree. But what I could do is ask you for a specific term. So just write this down. Don't try to answer it yet, just write it down. Just take a few seconds. Don't write down what you think the answer is, but talk amongst your pod members. What do you? How do you think the 6th term is going to look?
That's right.
Okay, I hear some really good arguments happening right now.
2 to 6.
This is what I'm hearing. I'm hearing you argue, is it 8 choose 6 or 8 choose 5? Riley, why is it 8 choose 5? Okay, if we go back to our binomial theorem, we start out with whatever choose 0. Right? So our first term is something choose 0. So in this case, our first term would be 8 choose 0. Our second term, 8 choose 1. So our sixth term is going to be 8 choose 5. Okay? From there, we have a to a power, and we have 2b to a power. What did I tell you about this number right here? And what did I tell you about the two powers combined? They add up to the n, which is 8. So this needs to be 3. No. These are lower. Okay, so somebody tell me, what is 8 choose 5?
56.
Okay. So we have 56 times a cubed 2 to the 5th.
32.
So what's 32 times 56? I heard some mumbles.
17.
Sorry, you guys said it, but like at different times, and so I heard. That's gross. It could be worse. That's all I'm gonna say.
It could be worse, like this one.
Just miss it.
But there's more.
Yes.
Find the coefficient of the term a to the 6th, b to the 5th. In the expansion, 3a minus 2b to the 11th. Just write it down. Don't think about it yet. Just write it down. Okay, so we know the power of A and the power of B, right? We also know what N is. So we know this is 11 combinations of something, and we know that we need 3A to a power and negative 2B to a power. Why is it negative 2B? Because we're subtracting. Okay, what does the power of A need to be? What does the power of B need to be? Okay, and if the power of B is 5, what does that mean about this guy right here? That better be 5. Okay, because this number is always going to match this exponent when we set up. All right, Max, throwing your pencil over there. What's 11 combinations of 5?
162.
Bailing them out. Okay. 3 to the 6th. And then negative 2 to the 5th would be negative 32.
Wait, you forgot the A.
Oh. There you go. Squeeze them in. Okay. So now what's 460 762 times 729 times negative 32.
You can all write that down.
Whoa, what did you say, Brown?
I got that.
536.
Yikes.
But I was only asking for the coefficient, so I only want that. See, Kinley, it could be worse. Okay. Any concerns you have?
No.
Okay. Are you thankful that I'm not going to make you multiply this out using distribution?
Yes.
Yeah, that's what we did last time. Yeah, that's when I started to cry.
When what?
Like when we had to like multiply it all out, like yeah. That's when the tears. They made us multiply it all out like year, and then a week later they're like, "Oh, wait, you're saying easy." We're like,
Well, because you got to understand where it comes from. Right.
It's like what brought us. I don't think